Welcome back everyone to Learning by Teaching. Today we're in dynamics and we're going to be solving problem 17.1. Okay, so new chapter today. It says determine the moment of inertia I sub y for the slender rod. The rod's density rho and cross-sectional area A are constant. Express the result in terms of the rod's total mass m. Okay, so as always I like to just start my problems by having some of the equations that the book gives us. And in this case, we're going to implement basically the first equation. So what we have in here is that our moment of inertia is going to be equal to the integral of the distance squared times the change in mass. Okay, so the first thing I thought when I was doing this problem, well, what is the change in mass? So the first thing I want to notice is that, well, mass is equal to our density times our volume. And if we further simplify this, we have that, well, it's rho times the area times our unit of length, which is usually a height, correct? So in this case, I'm going to use L. If I have a change in mass and the problem statement is telling me, hey, your rho, your density, and your area are constant, that means that my density and area cannot be the source of my change in mass. Therefore, it has to be my change in my length, okay? Which is, in this case, I'm going to use as the change in the x direction. And that is so because our length is from the y-axis in the direction of the x, okay? In the x direction. So that's the reason why I'm choosing the x. So if we're going to solve the problem, we're going to say, hey, the moment of inertia is going to be equal from 0 to L. And the reason for that is, well, how? We know that our distance is going to be from the y-axis all the way running to the x-axis. And my last point is this called L, okay? So my length. And then we're going to have, well, the distance square. Well, the distance from my y-axis to each point is going to be always x, so we're going to have x squared times my change in mass, which we figure out to be rho times the area times the change in x. Okay, so sorry, we should have an equal sign in there. So my moment of inertia has to be equal to, I'm going to pull out my rho and my area outside of my integral because they're constant, from 0 to L of x squared dx. Okay, and if I solve this integral, well, first of all, we have our rho and our area outside. And when we solve this integral of x squared, it's going to be x cubed divided by 3 with some boundaries from 0 to L. Okay, and if we compute these boundaries, we're going to have rho times my area multiplied by L cubed divided by 3. Okay, so we're going to plug in basically the L where the x is, and that's why my L cubed divided by 3. And then when we plug in 0, well, we have like 0 cubed divided by 3 is equal to 0. Therefore, my answer stays the same. Okay, now I want us to pay attention. We're really close to the final answer. And the reason for that is that they says, hey, express the results in terms of the rod's total mass. And right now we have our inertial moment of inertia not expressed in terms of the mass. But what we need to find out again is that, hey, my mass is equal to rho times the area times my length. And we have rho, area, and we have 3 lengths. So what we can say, hey, my answer, my final answer is going to be that the moment of inertia is equal to my mass times L squared, my length squared, all divided by 3. Okay, and finally, this will be my final answer. So I really hope you guys enjoyed the video. Please subscribe, push the like button, and I'll see you guys in the next one.